Hi, in this segment I'm going to introduce the two tasks of named entity recognition and information extraction, methods for getting simple structured information out of text documents. Let's start with information extraction. The goal of information extraction systems is to find and understand limited relevant parts of a text. And normally we're going to run it in a context where the system gathers information across many pieces of text. And the goal of doing this information gathering is to be able to produce some sort of structured representation of the relevant information. So you can think of it as instances of a database relation, so rows in a database table, or as a knowledge base. And when we do information extraction, we can have one of two goals. One goal is to directly help people to organize information so that it's useful to people. And the other possibility is to put the information in semantically precise form. So commonly, computers for other downstream information processing tasks won't be able to perform them if the input is just natural language text. But if we can have pulled out various kinds of relations, such as a database table, then it's very easy to do subsequent data mining and processing. So the kind of information that IE systems extract is clear factual information, the kind of who did what to whom, when kind of information. So let's take a look at an example of that. So here are a couple of examples. One's gathering earnings, profits, board members, headquarters, any of this kind of factual information about companies from company reports. So the idea is that the system can look through the text and then it sees, okay, here's the name of the company, and then it's talking about its headquarters, and it says that the headquarters are located in, so that's kind of an indicator of a headquarters location, Melbourne, Australia. And what we're going to get out of that then is this relation, which you can think of as an instance of a database table. That's only one example. There are lots of other examples. Another example is this one that I show here. There are lots of cases in biotext mining, so learning drug gene product interactions, learning subcellular localizations, lots of relations of interest to bioscientists in various ways have been worked on in information extraction systems. In the more consumer space, information extraction is now available and I think popular in various applications like either Apple or Google Mail, or is used in web indexing. So here's a little example from Apple Mail, and so here there's this date, and so Apple Mail recognized that there was a date there and put in that little arrow box. And when I hold that down, it's then offering to create a calendar event for me. And so that's kind of a little help of now allowing me to do that kind of task faster. This kind of information extraction is often fairly simple and seems to be mainly based on using the kind of regular expressions that we saw earlier, including name lists. Here's one more example about how companies are starting to surface information extraction and search applications. So if I stick into Google BHP Billiton headquarters, as well as regular web search results, that is actually giving me right here, best guess for headquarters is Melbourne, London. Of course, we can argue a little about whether that's the perfect answer. They're really kind of two separate answers here. BHP Billiton's actually kind of a complex case because they have this complicated dual company structure, and there is a Melbourne office and a London office. So we'll call that, just about correct. Okay, that was information extraction. Let me now go on and look at a particular subtask that has become very important, named entity recognition. So the idea of named entity recognition is that we're going to, in particular, just look for and classify names in a text. So the first step is we find names. So here we've then found a name, and in particular what that means is we're finding the limits of the name. So this one is these two tokens, this name is this one token, and then once we've done that, we're going to classify the names So we're going to say that this name here is a person name, this here is the name of an organization, this is a date, and then we have a sequence of further person names. Sorry, I guess this one's Rob Oakeshott and goes across the line break. So to say a little bit more precisely what the task is, we have this sort of phrase of named entity recognition, and it's a little bit of a code word these days that reflects the history. The idea of it was that entities were meant to refer to discrete things in the world. So I am an entity, Stanford University is an entity, but something like sand or air isn't an entity, that there's not a specific delineated physical thing. And then the idea of named were that some entities have names. So I, Christopher Manning, have a name, but the chair I am sitting in as I record this, it is also an entity. It's a discrete physical thing, but it doesn't actually have a name attached to it, so it's not a named entity. That's the kind of philosophical history. In practice, as the word is used in named entity recognition, that's not quite what it means, because effectively what we're doing is using named entity recognition to mean easily distinguishable names or other things in text that we can pick out. So in particular, 2010, so things like dates, times, quantities are normally regarded as named entities, although according to the original starting point of the name, something like a date or a chemical or a protein isn't actually an entity at all, but we always include those kinds of things when we're building named entity recognition systems. Okay, so what is the use of named entity recognition systems? Well, named entities, if you identify them in a text, they're something that can be indexed or linked off. So as I note down below, many companies make use of various techniques for tagging entities on web pages, and then they can provide links off of those entities to bio pages or topic pages or other things of that sort. So there are a whole bunch of commercial products that run as web services that allow you to do that kind of thing. If in general you want to be crawling the web and picking up sentiment, we discussed earlier detecting sentiment as to whether it's positive or negative, but you will then also need to work out who the sentiment is about or what the sentiment is about. And so at that point you need to be picking out the company or product names in the text, and that's a task of named entity recognition. But there are a lot of other uses where named entity recognition is a subcomponent of a larger task. And so commonly, when you're doing information extraction, a lot of what you're doing is actually identifying named entities and then working out the relationship between them. So we'll talk later about question answering. And in question answering, for various kinds of questions, often the answers are named entities. When did something happen or who did something? And so it helps a lot for question answering if you have good named entity extraction. Another example that we also saw of how people use named entity recognition that plays off this having semantically interpreted information is to use it in then various kinds of things like calendaring applications where you're making use of the semantic interpretation.
Okay, so the next topic that we're going to talk about is machine translation. Machine translation is one of the most exciting areas of natural language processing research. So why is it important? Well, there are more than 7,000 languages in the world. It turns out that the majority of the documents, however, on the web are in English. So as you can see from this diagram, about 55% are in English. Then you have small segments in languages like Russian, German, Spanish, Chinese, and French, and smaller percentages in other languages. So the remaining close to 7,000 languages have only 11%. This is in stark contrast with the number of internet users in the world. So in that second diagram, you can see that English and Chinese speakers form the majority of internet users, followed by Spanish and Japanese and so on. And the percentage for speakers of other languages, the languages that are not in the top 10, goes up to 17%. So since most of those people speak only one or maximum of two languages, it is very common that they would encounter a document on the web that is in a language other than their own. So for that to be avoided, we need to come up with ways to translate text automatically. So this is exactly what machine translation does. So let me show you now a little picture. This is a famous painting by Peter Bruegel, the famous painter from 1563, depicting the Tower of Babel. So there's a biblical story that says that people were only speaking one language at the time, and then when they built the Tower of Babel, God created all the different languages so people couldn't talk to each other so easily. So we are trying to solve this problem now by creating machine translation systems. Okay, so now let's see how machine translation works. So most of the modern translation software is based on statistics, and I'm going to show you as an example the so-called Rosetta Stone, which illustrates how statistics can be used to translate languages. So here's what the Rosetta Stone looks like. It has inscriptions in 3 languages, one of which is shown here. This is Egyptian, and then at the top, and then Greek in the middle. This stone was carved in Egypt in 196 BC, and it was only deciphered by contemporary humans by Champollion in 1822. And the way he deciphered it was to figure out that those texts, even though they were in different languages, were translations of one another. And he was able to figure out, using some pattern recognition, or manual pattern recognition, which symbols in one of the languages matched which symbols in the other language. So if you're interested in the Rosetta Stone in more detail, you can go to this website and look at the entire text and the alignments. So here's a NACLO problem that is very similar to the Rosetta Stone. In fact, this category of problems in NACLO is called the Rosetta Stone problems. It was written by Simon Schwartz based on work by Kevin Knight. So here's what the problem looks like. It is not about a real human language, although there is a little twist to what I just said, which I'm going to explain in a few minutes. So instead, we're going to focus on the story described in this problem, specifically that this is about Arcturan, which is a intergalactic language. And you have come up with some communication from a foreign constellation in this language. And you know that each sentence on the left is in the Centauri language, and each sentence on the right is in the Arcturan language. And now the question is, can you figure out which word in one of the languages matches which word in the other language? So how would you do this? So I'm going to let you think, and you can do this by looking at the next couple of slides, and then I'm going to show you the answer. So the specific task in NACLO was to find individual words. So for example, the word Farok in Centauri. So that word appears in 2 of the sentences. And then what you need to do is to figure out which sentences in Arcturan those correspond to, and see if there is one single word in those 2 sentences that appears only in them and not in any of the other sentences. So you can continue doing this for the other sentences and the other words until you have unique translations. And here's the solution. It turns out that even though those languages were labeled as Centauri and Arcturan, they're in fact English and Spanish, and this is the example that was used by Kevin Knight in 1997 to introduce how machine translation works. So every word in English and Spanish was translated into some made-up word in those artificial languages. And now you can see that it makes more sense. So for example, the word Garcia appears in both languages, English and Spanish. And since this is a person's name, we can use the principle that person names are typically left untranslated. So we can figure out that the word woon in the two languages is the same. And you can do this recursively until we figure out the rest of the words. Okay, here's the full solution. Okay, so you probably now have an idea how machine translation, or statistical machine translation rather, works. You need to have what is known as parallel corpora. So a parallel corpus is a text in one language that is aligned to a text in another language that forms its translation. So there are many instances of parallel corpora around there. The first one is the Rosetta Stone, which is obviously very short. Then there is data like the Hansard's corpus. So the Hansard's corpus is the proceedings of the Canadian Parliament, which by law has to keep all parliamentary proceedings in both French and English, which are equally official. So every time somebody speaks in English, there is a translation done by humans in French and vice versa. And since this is government data, it can be obtained very easily from the Hansard's website. And most of the early statistical machine translation systems were trained using this kind of data for French and English. There are many other parallel corpora available, for example, news stories that are translated in different languages, user manuals that a certain company publishes so that people in different countries can use their products. One of the most common data sets used for machine translation training, which is available in thousands of languages, is the Bible. So let's look at some examples. The Hansards, here's an English paragraph, 2 sentences, and their translations in French. So I'll just give you an example of words that are aligned here. So government in English appears as gouvernement in French. So that's a fairly straightforward example, which also forms a cognate, or the two words have the same historical connection. Now the next thing is Postmaster General, which gets translated as Le Ministre des Postes, or in other words, the Minister of Posts. So that's not exactly the same translation as Postmaster General, but it means the same person. So you can see that even though those documents refer to the same person in both languages, they may use some very idiosyncratic vocabulary that is not directly translatable. So here's one more example from a Bible paragraph in English and its translation in Cebuano, which is a language from the Philippines. So let's try to figure out how we can translate those 3 words, God, heaven, and earth, from English to Cebuano. So here's one pair of aligned sentences, then another one, and then a third one. Now, we can use a lot of information. First of all, Cebuano is spoken in the Philippines. In the Philippines, Spanish used to be a commonly spoken language, so there are some words in Cebuano that are cognates. So, for example, Dios here, if you know Spanish, you can immediately figure out that it means God. But that's not the basic idea of statistical machine translation. What's more important is to look at co-occurrence statistics. So we're looking for words that appear in the same sentences in both languages and don't appear in any of the others. So for example, here, I'm going to let you pause for a moment to figure this out. Can you figure out what are the translations for heaven and for earth, just based on those three examples? So here's some of the information that you can use. Co-occurrence in sentences, word order, especially among across languages that are relatively similar to each other, which is probably not the case here. And also cognates, which again is more useful when the languages are related. So you need to have corpora of this nature that are aligned at the sentence level. If those are not aligned, then the first thing that you need to do for this algorithm to work is to align them automatically. Well, if they are exactly the same text, alignment actually can be done. But if they are not exactly the same text, they may be just what is known as comparable corpora, then sentence alignment may be much trickier and noisier. But it is still possible to use it and build translation systems purely based on comparable corpora. So here's a NACLO problem that you can download. It's about language similarity. You can see how often you can identify cognates among languages that are historically related. So you have the first sentence of the Universal Declaration of Human Rights in 17 different languages, and you have to figure out which ones of those are in the same language family, because they have very similar words. So the first 11 of them are shown on this slide, and 2 of the languages are labeled as English and Latin, and then you have 6 more on the second slide. So you should pause here and look at the last 2 slides and see if you can figure out which of those languages belong to the same family. So the answer will be shown next. So here are the 7 clusters. You can look up the Universal Declaration of Human Rights on the internet to figure out which specific languages we have here, but they include languages like Romanian and Italian and Basque and Latvian and so on.
Okay, so in this next segment of the class, we're going to talk about the IBM translation models. The IBM models go back to the late 1980s, early 1990s. They were seminal in really starting the whole statistical approach to the translation problem. They form a central part of modern statistical translation systems, and so we'll cover these models in some detail in this segment of the class. So just to recap, this is a slide from the last segment of this class. This is a recap of the noisy channel model, which was introduced by the IBM researchers to translation. So a noisy channel model, as we said, has two components. Firstly, P of E. This is a language model. This is a model that assigns a probability to any sentence in English. And secondly, P of F given E. So this is what's called the translation model. This assigns the model for a French sentence given an English sentence. One note, throughout this lecture I'll follow convention, which is I'll always assume that we're translating from a French sentence to an English sentence. So that is our goal. Okay. Of course, we might have other languages we're translating between, but for the purposes of this lecture, we'll always assume we're translating from French to English. Okay, so we have a language model for strings in English. We have the translation model, which, as I said, is in a sense backwards. It says what's the conditional probability of any French sentence given an English sentence. When we translate under this model, we search for the English sentence that maximizes the product of P of E and P of F given E. And so when we evaluate for a particular sentence F, different English translations, we take both of these terms into account. So the roadmap for the next few lectures in this course on translation is as follows. I'm first going to describe IBM models 1 and 2. So IBM went through a series of models, I think 1 through 5, and we're just going to do the first 2 because they will essentially introduce many of the important ideas, and actually model 2 is a pretty decent model for the problem we're going to be looking at. We'll then go on to describe phrase-based models. So phrase-based models were invented around the late 1990s, and they're in some sense a second generation of statistical translation systems. This is the first generation. They make direct use of ideas from these IBM models, and so these IBM models will in some sense form the basis of phrase-based models. But phrase-based models work much, much better than the IBM models. They do, in fact, form the basis of many modern statistical translation systems. So, for example, Google Translate is heavily built on this technology.